once again. Good. So the agenda for the rest of the afternoon is to talk about algebraic lattices and learning with errors over rings, ring LWE. And I'll start by just reminding you what we did last hour, which is learning with errors. Okay, so we have the dimension n and the modulus q and an error rate. And solver is, the adversary is given these random noisy products with a secret vector. And the goal is to either find the secret or to distinguish the noisy products from the uniform products. Okay. And we've seen that LWE is hard. It's got these quantum or classical worst case to average case reductions. And these then can be used to get cryptography. So that's the summary slide from last time. And LWE and also SIS are rather efficient. Well, they're sort of efficient. So from the standards of much cryptography historically, they're quite efficient. For example, if you want to get one pseudorandom number, so a scalar bi modulo q, then, well, what does this cost you, right? It costs you one inner product. So you have your secret, you have the vector ai, and then you just take the inner product of these two, and you add some error to it, and that gives you a pseudorandom scalar. Right? So this bi looks like it's random, even though it's basically the inner product of a and s. Okay, so that's pretty cheap, right? Pretty good for a pseudorandom generator. And in fact, it's even better than this. We can amortize each of these vectors ai over many different secrets. So there's a simple hybrid argument showing that you can do that. And you can also amortize, well, it's already in the definition of LWE. For a single secret, you amortize over many different A's as well. But more interestingly, for each AI, we can have many different fixed secrets in advance to get even more scalars, pseudorandom scalars out. But still, you have to do quasi-linear work per scalar output. Good. A rather unfortunate, though, disadvantage of LWE and SIS is that the cryptosystems we use, they have rather large keys and ciphertexts. Okay, so inherently, in the system that I showed you, the cryptosystem from last time, you've got this public key, which is this like n by m matrix. And in addition, the ciphertext is at least linear in the dimension, right? So at least a linear in n in its dimension. So inherently, you've got a quadratic amount of time required to encrypt and decrypt a message. You have to multiply this matrix times some secret and do quadratic work even to encrypt or decrypt a single bit. So that's a little bit worse than the story I'm telling up top, which is just cost you an inner product. So good. So quadratic is not terrible, compared to modular exponentiation or elliptic curve operations. It's actually rather cheap. But in practice, the n here can be quite large. It has to be in the many hundreds or even thousands or more. And so quadratic is rather expensive at least for very high efficiency needs. So that's something of a disadvantage of LWE and SIS. So this can kind of raise your thinking. Like if you're not satisfied with the efficiency that it has, you can maybe start thinking and imagining maybe we could do better. And here's one thing you might hope for. Instead of to create a pseudorandom value, instead of just doing an inner product, what if there was some other kind of product operation that we could do where we take a vector A and the secret S, and then we apply some kind of other product, which doesn't give us a scalar anymore, it gives us a vector. Okay, so what if it gives us a vector, say, of the same dimension? And then we add some error vector to that vector, and we get now a BI vector there. Right? So what that would do, while we're imagining, is that it would give us n pseudorandom scalar values, right? This whole vector, like an n-dimensional vector here, which would hopefully be pseudorandom, using just one hopefully cheap product operation between A and S, and then plus the addition of the error. Okay, so like that would be a dream, right? And so the question is, well, if you want this, how could you define this product operation so that it really is secure, so that the AI-BI pairs are really pseudorandom, so that you can use all the nice properties of decision LWE and all the constructions from it. And you have to be careful, very careful with this. It turns out that in the usual case where we talk about small error, for example, coordinate-wise multiplication of vectors is completely insecure. So you can solve LWE very easily if this star operation is just the Hadamard product, coordinate-wise multiplication. So I'll leave that as a little exercise, but it's quite straightforward to do. Okay, so that becomes insecure. So okay, well that product operation doesn't work, but maybe there's something else that we could use, perhaps. And in fact, there is. So the kind of the theme of the talk today will be describing exactly what kinds of products we can use so that we do get some kind of meaningful hardness and security. And so the answer that we give is that the the star product will be instead corresponding to multiplication in like a polynomial ring, for example. So for example, consider the ring ZQX modulo some polynomial, some fixed polynomial ring. Yes, and yeah. Okay, so in fact, this is a very fast operation. You can do this kind of multiplication very efficiently using, for example, fast Fourier transform. So you can do it in n log n scalar operations, and that's essentially linear time to do this product, which gives you now a linear psi set. So this is not our answer. In fact, this idea of using rings, polynomial rings, or ring structures like these goes all the way back to the n-true crypto system of Hofstein, Pfeiffer, and Silverman from 1998, and then was picked up and used in Daniele's work introducing these compact one-way functions based on what's now known as ring SIS and collision risk functions and so forth. Right, so this idea was used in n-true, which is doesn't have any kind of provable or worst case security reductions behind it, but then it has been used also in SIS type constructions or SIS type definitions, but hadn't been done for LWE until much later. So yes, you come in.
Before we move into polynomials, which I guess will be would it be possible to get this type of efficiency improvement using general lattices by amortizing both over A and S? Think of square matrices. If we had n square matrix multiplication algorithm, would that give n square to the random bits with a computational cost that is also n square, so it's still
yes. So right. So by the amortization trick, you can certainly turn these multiplications into like matrix mults and then use fast matrix multiplication. For very big dimensions, matrix multiplication can be faster. And asymptotically, it's 2.3 whatever, I think now, right? It still doesn't get you below the quadratic barrier, right? So the amount of work required to do encryption would still be inherently quadratic in the dimension. In fact, it would be more than that. It'd be matrix mults. Right. So the whole hope, or the whole thing that I'm going to be talking about is getting us well below quadratic. And that's the barrier you simply can't go below with standard LWE.
So Chris, you could potentially use fast rectangular matrix multiplication. All that doesn't.
Yeah, but I mean, just the size of the thing is quadratic, so you can't even read the key in less than quadratic time.
Amount of randomness, right?
Yeah, that's right. So maybe the amortized work would be perhaps sublinear in terms of the amount of work rating. Here, the amortized, what we'll do is something with an amortized work of like constant or tilde soft O of constant.
The point is quadratic in what, right? The answer is the
security parameter.
The security parameter, yeah, or the dimension, yeah. That's right. Yeah. So. You'll be doing at least quadratic work in the security parameter, and even amortized, it's going to be more than constant or more than polylog. And now we'll do linear, quasi-linear, and quasi-constant amortized.
Even if it was working, the plain text would still be quadratic in the security parameter to make it worse. The amortization would kick in only for plain text sizes that are quadratic in the
Sure. Yeah, also, well, let's see. You could maybe make them kick in at linear sized messages if you used like n by square root n or something like this.
And then square root n would be the security parameter.
No, n would be still the security parameter because the secrets would be dimension n. You'd have square root n of them.
I think to make rectangular matrix multiplication work, you need the other way around, right? You have like a anyway.
Okay. Yeah.
Offline.
Yeah.
The issue is the cost of breaking the crypto system, which is 2 to the n. It's not that using matrices brings the cost of breaking it to the n squared.
That's the point.
That's true. Right. Okay. So what we're going to do is use ideas like this, using polynomial rings and so forth, and fast operations in them to get us, by any metric below the quadratic barrier. But the focus will be on how to actually define a secure LWE in this setting and actually prove something about it. Okay. So in summary. This used to be a relevant meme, but okay. So I'll give 2 slides defining LWE over rings. One will be a very simplified, concrete version, and then the other will be the general definition, which will introduce some subtleties. So if you remember nothing else from the talk, I hope you take away this definition, and then depending on how awake you feel and how much number theory you want to do, you can remember the general version. So here's the oversimplified version. Let's choose a ring, this following ring. So this is the ring of integer polynomials modulo x to the n plus 1. And n will be a power of 2 here. Okay, so what this means is, every element of this ring can be represented as a polynomial of degree less than n, just by dividing by x to the n plus 1 and taking the remainder. Right? And concretely, what that means is you replace x to the n by -1, and you replace x to the n plus 1 by -x, and so forth. Right? So everything kind of wraps around, folds over, so that the degree stays below n. Right? Okay, good. And then we'll write r sub q as the quotient of r mod qr. So what that means is simply that these coefficients now are modulo q integers. Okay, so that's our ring. Well, I guess there's 2 rings here. There's the ordinary ring and then the ring modulo q. Okay, so, I just said it. So elements of RQ are simply polynomials, or can be seen as polynomials of degree less than n with modulo q coefficients. And we can do very fast multiplication in this ring using FFT. Okay, so as with regular LWE, there are 2 flavors of ring LWE. There's a search version and a decision version. And they look very similar to regular LWE, but here's how they're defined now. So in search, we have a secret ring element, S, as before. And now this is an element of R sub q. So again, S is a polynomial of bounded degree with mod q coefficients. And now the attacker is given pairs, noisy, random ring products now. So not noisy inner products, but noisy ring products. So concretely, we choose a random A1 from the ring mod Q, and then we give the attacker S times A plus some error. Now, what's a bit different or an important difference here is that S times A is now a polynomial, right? It's S times A. We reduce mod x to the n plus 1. So it's again a polynomial. We need to add an error polynomial. So what that means is there's some error to be added in like each coefficient of that polynomial. Right? So you can imagine it looking something like this. It's kind of an n-dimensional error that we draw from the ring. And again, as before, we have some error parameter alpha q, or some of the width of the error in each kind of in each coordinate, essentially. Okay, so that's what a random noisy ring product is, and you can give several such products to the attacker, and then the goal of the attacker is to find the ring element S. Now, as before, with plain LWE, if you didn't have the errors, this problem would be easy. And is it so clear that this problem is easy if you don't have any error added in? Anyone see how to break it?
Consider the polynomial A as its matrix form and without the error.
Okay, good, yeah. So one thing you could do is just consider the polynomial A in its matrix form. So multiplication by A corresponds to a matrix, which you can expand out. And then to solve for this, well, you just have to multiply by the inverse of that matrix. One subtlety is that inverse has to exist. And it turns out that with high likelihood, this AI will be invertible. But if it isn't, you can handle the there's some linear dependencies. You can throw out the dependent vectors, and maybe one more sample you need to get the full linear independent set. So yes, so without the errors, linear algebra is the answer. But really, it's just division by A in the ring, assuming it's invertible. Okay, but it's what the errors is what makes this hard, again, as we've seen before. Okay, and then decision is the same, kind of the same story. You're given a bunch of pairs, which are either generated in this way or are just uniformly random pairs, and you just have to decide which it is with some good advantage. So any question so far about this concrete definition? Well, one here and then there.
So should I see already at this point that we have savings? It just seems like you've written the matrix product in a different form, so it's unclear why you get...
Right. Yeah, so where's the savings here, right? So as was already mentioned, an element here of the ring kind of stands in for a square matrix, right? So multiplying by A can be seen as a linear transformation, and so it's standing in for an n by n matrix. But this is much more compact, right? This is only n coefficients, and it's basically standing in for n LWE samples. And so this one n-dimensional vector or polynomial is now replacing an n by n matrix with an n separate LWE samples. So we're getting a factor of n savings in the space. We're also getting a factor of n savings in the multiplication, because we can do this multiplication in quasi-linear time as opposed to a square matrix times a vector, which would be quadratic time.
And then why do we have like A1, A2, A3? It's just like, it's just for illustrating the decision problem, or?
Can you say again?
These A1, A2, A3 don't correspond to like the coordinates as before of these vectors.
Oh, right. Good. So this A1 is it's a full polynomial, and then A2 is a uniformly independent random polynomial.
So in the crypto system, I just should think that A1 is the like the public key or something, and
right.
No A2, it's just a fixed thing.
Yeah. So depending on what crypto system you're talking about, there may only be a single A1, or there might be a few of them. But certainly, generally speaking, we only have a small number of such polynomials in a crypto system. That's
The
right.
way it's presented here, you need at least 2 samples, otherwise it doesn't really make sense.
2 samples to make it uniquely defined, probably, yeah. Okay, question over here?
How do things change if you quotient out by different polynomials? Like if
Yes.
n is to the power of 2?
Yeah, so I'll go to, that's the next slide, which is the general form of the problem. Yeah, so right now I've picked a very particular polynomial here. The reason why is this is what is known as a cyclotomic polynomial, and it's known as the 2nth cyclotomic polynomial. So the roots of this polynomial are the 2nth primitive roots of unity, which has a number of nice properties. For example, this is irreducible. This is an irreducible polynomial, and all its roots are roots of unity. And so we'll see many advantages of that later in the talk.
So can you work with reducible polynomials then?
So reducible polynomials can be a problem. They can be a problem for security. You can define whatever you want, but the question we are focused on is what is secure, right? Yeah. Yes.
Sorry, maybe it's a silly question, but going back to the case where you don't have any error added, I'm trying to solve, to distinguish. How do I know that I won? Would it be because the distribution of S is uniform while the distribution of B times A inverse?
Good. Okay. So good. So the question is, if there's no errors, and looking at the decision problem, how do you know if you've guessed correctly? How do you know if you've yeah. So imagine that you have 2 samples or 3 samples. You can divide this one by that. You get a candidate S, and then you check whether that's consistent with the second sample. If they're consistent, you know that you're in this case. If they're inconsistent, you're in this case. So you basically have a perfect distinguisher. Okay. Other questions about the setup here? All right. Very good. Okay. So now let's see more generally how to define this, and there's some very interesting things that come up when defining it. So the way we've defined it after a lot of different, basically playing with a lot of different options, is that we focus on the case where the ring is what's known as the ring of integers of a number field K. If you know what that is, great. If you don't know what that is, it's enough to say that oftentimes such a ring is Zx modulo some f of x, which is irreducible, okay? Irreducible over integers. So let's just focus on this case for today. This is already a rich enough class. So we have the polynomials, integer polynomials modulo some irreducible polynomial f of degree n. And so that will be our ring. And a very important object is that this ring has what's known as a dual ideal, or it's actually a fractional ideal, but there's an ideal which we'll call R dual, or RV. And this is a dual ideal with respect to a certain geometry, which we'll define shortly. So this is an important object which goes into the definition of the problem. But for now, just imagine that there's this ideal RV, which is essentially an ideal of R. Okay. So again, we have an integer modulus, and RQ is the same. It's R mod QR. So now all the coefficients are mod Q. And then RV mod Q is analogously defined here. So it's the quotient of RV mod QRV. Okay. Then again, we have a Gaussian error of appropriate width. And this is how the problem is defined. So again, with search, we have a secret element. This element S actually belongs to the dual ideal mod Q. So you pick an element from the dual ideal, and then you get you give independent samples AI and AI times S plus error. Okay. So one thing to notice is that when you sample this AI from the ring, and when you multiply A times S, well, because this is an ideal, the product lives in RV. Everything's mod Q. Right? So this is this product here lives in RV mod Q, and you add some error to it. So here's a kind of a picture of an alternative scenario where this is the shape of RV. So RV as itself can be seen as a lattice. There's a way we'll see how to do that. And so when you see it as a lattice, it may not be a nice, rectangular or square lattice. It may look hexagonal or something like that. And so this is what the picture would look like there. But basically, your products A times S, you end up in a lattice point here, and then you add some error to it to kind of blur it around. Okay. So yes, question.
Do the technicalities appear for security or for efficiency?
Yes and yes. So it turns out they benefit both for the security proofs, for the efficiency of the crypto systems, and I want to say a third reason, but those are the only 2 reasons I can make. I guess just for the general elegance of the definitions as well. So yeah, it kind of all comes together in a win-win-win type of situation when defined in this way. Yes?
Why do you say it's better in terms of security to define it this way?
Well, we can get the worst case to average case reductions will be better this way. They'll give, It'll be tighter in terms of the approximation factor that you get for I should convince you offline of that. Okay, and then decision is the same way. Oh, was there another question? Yes.
Just checking that, so if we specialize to the case we had previously, this dual ideal is just going to be the...
Yeah, great question. Okay, so in the previous case, where f is x to the n plus 1 and a power of 2, the dual ideal, I can tell you, is actually equal to r, but with a n in the denominator. So it's just a scale down of r. It's 1 over n times r. It turns out. So good. It's a great question, which is why the simplified definition I gave did not need the dual ideal, because RV and R are the same up to a scaling factor.
Where does this n come from? Because isn't the ring of integers of the cyclotomic just Zn?
It is, so it's Z join the root of unity. Yeah, so the dual ideal is just a shrinking, scaling down of R. And you can scale back up if you wish. There's no loss in doing that. Okay, so yeah, so this is the general definition. Other questions about this? These are great questions. Okay, so with this definition now we can state some hardness theorems. There's kind of two hardness theorems that we'll focus on. So there's the initial ones that we proved in 2010 in this paper, and then there's a subsequent one which addresses some gaps in the first one. So the nature of the initial reductions are as follows. We have a worst case to average case reduction from approximate shortest vector problem on arbitrary ideal lattices of the ring. I'll tell you what ideal lattices are. And what the reduction says is, if you have an algorithm for solving search ring LWE, then you get an algorithm for approximating SVP in arbitrary ideal lattices of the ring. And as noticed before, this is just as before, this is a quantum algorithm, quantum reduction. This reduction works, though, for any ring of integers in any number field. So completely general with regard to the choice of ring. So that gets you from worst case problems to search ring LWE. And then analogously to with the regular LWE scenario, we have a search to decision reduction. It turns out this is much, much trickier to do than in the plain LWE setting. And it's basically because decision asks that like all n, the entire B polynomial be pseudorandom. So there's a lot of pseudorandom scalars that you need in there. They should look like a completely random vector. So that requires a lot more work. And in particular, we were only able to get this for the cyclotomic rings. So, but it was classical. So this link here is classical, but it's for a restricted, very restricted special class of rings.
The left inequalities were the in the previous represented.
Yes? No.
Damien.
This wasn't even defined.
Sorry, what was not defined?
No, I mean.
LWE, not RLWE, but.
Well, so this is for any ring.
Sure.
Independent.
Yeah.
Okay, so then there's a newer reduction which says, well, it gets rid of this in the middle. So the problem is going from here to here, restricted to classical, cyclotomic rings. And that was unfortunate. We didn't want to be so restricted. So we said, well, what if we could just go from here to here directly? And in fact, that's what it does. So the same thing on the left here as up here. This is quantum, works for any ring, and it just goes directly to decision ring. So if you want hardness of decision, you don't need to limit yourself to these cyclotomics. Okay. And then, well, as usual, if you assume decision hard, you can build a lot of cryptosystems. In fact, almost, well, I'll say most Crypto systems from LWE pretty straightforwardly port over to ring LWE. You often have to check, do all the things in the proof work out? Sometimes they do, sometimes they don't, but often they do.
And Chris, the other way around as well, most of the time.
The other way around, always, I think. Yeah, because ring LWE is a special case of LWE. So I think they could port from ring LWE to.
Some of these could assume more structure. I have one application which could assume.
Oh, no, I see.
It's not obvious that.
I see what you mean.
It's not obvious why you would want to do it if all you care about is efficiency. You're actually making it worse. But if you care about assumptions, then
yeah, I see.
you don't want to put a ring on it.
Okay.
Sometimes you don't.
We don't want to take a ring off of it, I guess. Okay, so let me say a little bit more about this geometry. So when we have a ring that looks like this, the goal is to give it a geometry and to get lattices from this. So for example, when you have zx mod f of x and f is irreducible, then this f has n different roots. Call them alpha I. And so there are, what's known is that there's exactly n different ring embeddings or injective homomorphisms from this ring into the complex numbers. And these homomorphisms are just given by evaluating the polynomial at a particular root of f. So if you take this polynomial and just evaluate it at alpha I, then that gives you a complex number. And this is a ring homomorphism. So adding two polynomials, of course, the results are added. Multiplying two polynomials, the results are also added. This is because you can add or subtract multiples of f, and the result is it vanishes, right? Because f of alpha is 0. So good. So we have these n embeddings, ring embeddings, and so what's known as the canonical embedding or Minkowski embedding of the ring into the n-dimensional complex numbers is to just apply all of these n embeddings in some fixed sequence. So just sigma of a is just applying a to all of the n roots, one after the other. And this is a very useful way of getting a geometry. This goes all the way back to the 1800s, I think, in algebraic number theory, where we can basically define geometric quantities on the ring via this canonical embedding. Right? So when I talk about like the Euclidean norm of A, I really mean the Euclidean norm of its embedding into c to the n. And we can also get lattices. So in particular, the ring R embeds as a lattice. In fact, any ideal embeds as a lattice into this space.
What's A here? What's A and B?
Oh, A here or here?
What is the definition of A?
So these A and B are elements of the ring. Yeah. Right. So this sigma here, this canonical embedding, is very nice. It's got a lot of nice properties. Both addition and multiplication map to coordinate-wise addition and multiplication under the embedding. And that's just because each of these is a ring homomorphism. Okay, so if the embedding of the product is just the coordinate-wise product of the embeddings. Same for sum. Okay, so one useful consequence of this is that it gives us what's known as an expansion bound. It tells you how big can the product of two ring elements be relative to the original two elements. Right? So in particular, if you want to know the Euclidean norm of A times B, well, that's at most the infinity norm or max norm of A times the Euclidean norm of B, or switch the roles. It's commutative. So this A sub infinity can be seen as like the expansion of A under multiplication. Okay, so we can get bounds like this. They actually apply more generally. This applies to any P norm, not just the 2 norm. So you can understand multiplication and addition very nicely through this embedding. Okay, and this expansion is element specific, right? It's just determined by the particular A. It's not a global property or anything. Okay, so let me do 2 examples. Okay, they're both pretty simple examples, but they show a little bit of the variety that you can encounter here. So in one example, let's use a power of 2 cyclotomic, which is what I started with originally, but I can only use the x squared here. I can't go in a higher dimension. This is the most I have room for. So the 4th cyclotomic is this, and the embeddings just map x to plus or minus square root minus 1, which are the roots of that polynomial. So when you do the embedding, well, it's enough to see, let's just embed the element 1 and the element x. And so here you get 1, 1, and here you get plus I and minus I. So I guess I would normally need 4 dimensions, but it lies in a 2-dimensional subspace. So it looks basically like this if you apply the right subspace. So this is the lattice, right? The ring here embeds as this lattice, which is just a rotated square lattice here. Good. And more generally, in power of 2 cyclotomic, which was the key case of interest from before, we have the following nice things. Every power of x has Euclidean norm n because it has infinity norm equal to 1. Both are true. So all these powers of x, when you apply the embedding, they all become roots of unity. So you just have a vector, which is all its entries are roots of unity. So you get this these bounds, or these equalities. Okay, and in fact, more generally, the picture is very similar to what we see here. This power basis, the power is 1, x, all the way up to x to the n minus 1, embeds as an orthogonal basis. So these vectors are pairwise orthogonal, and they all have length square root n. So really, this is just a square lattice that's kind of, it's a rotation and a scaling of the integer lattice. But it's essentially the integer lattice with no, at least geometric. Okay. So any question about this? This is for power of 2 cyclotomics. We can look at one more example, which is slightly more interesting. The 3rd cyclotomic looks like this. So this is now the polynomial modulus, and the roots of it are, let's see, -1 plus or minus square root -3 over 2. So now the lattice embeds to something like this. 1 embeds as 1, 1, but x embeds as this thing, and the angle between these is 120 degrees. So you get this hexagonal lattice instead. And but still, many of the nice properties that we saw for power of 2 cyclotomics still hold here. So again, all these powers of x, when you embed them, they have Euclidean norm 1, and they have expansion. Euclidean norm root n, and expansion equal to 1, just as before. The power basis is now not orthogonal in the non-power of 2 case. But maybe that's OK. We have a way of dealing with it. So one consequence of this is that elements which are short might have large coefficients relative to this basis. So for example, if you look at this vector here, it's just as short as these vectors. Right? It has exactly the same length, but its coefficient vector is 1, 1. So there's some distortion between like the polynomial written as a vector of coefficients and the actual length or shape of that under the embedding. Okay, so any question about these examples here? So now let me define this dual ideal duality, which plays such a role in the ring LDB problem. So there's a function called the trace, which maps from the ring into the ordinary rational integers. And, oh, the macro broke. OK, this is trace of A. So trace of A is just the sum of A's embeddings. So this is going to be for the cyclotomic case here. So we take all the embeddings, just sum up the embeddings. And then the trace of A times B is essentially like the inner product of the embedded A and B. So this trace product between any 2 elements is basically acting like inner product.
Trivially, the output of the trace is an integer?
No, it's not trivial. That requires proof. But fortunately, that was proved in the 1800s.
Okay.
Yeah. It's I don't know how easy it is to see. I don't have a proof in it. That's the top of my mind. It's not too hard to see, but it's not obvious.
Sorry, what was the question? Is it always an integer?
The trace of a ring element is an integer. Yeah.
How do you show that?
So one way you can show it is by writing the element as a matrix, fix some basis, and write it as a matrix for multiplication, and then the trace of that matrix is the trace of the element. Yeah, that's one way to prove it. Okay, so you can think of this trace product of trace A times B as the inner product of A and B. And then the dual, like for any ring or any ideal, you can define a dual of it using the ordinary definition of duality. But we'll use that. We'll use the trace product instead. So trace of A times D should be an integer for all A's in the ring. So pictorially, this corresponds exactly to the dual lattice when you apply the embedding. Right? So if we embed R, we get this lattice here. And then the dual lattice looks exactly like this. And this is a case of a power of 2 cyclotomic. Everything's orthogonal. And therefore, the dual lattice is also orthogonal, but it's scaled down by a factor of n. Okay, so that's a question before. So R looks like this. RV looks like this. It's actually just 1/2 of R. Here's the other example. So the third cyclotomic is now this like hexagonal looking lattice, and this is the dual lattice here. And for example, these two vectors are the dual basis of these two basis vectors here. So and then another interesting fact is actually RV is a superlattice of R. So every element of R is itself in RV, but in general, it's a very sparse sublattice of RV. Okay, so these are just pictures and the definition of RV. Again, it just corresponds to the dual lattice when you apply this canonical embedding. Okay, so probably just skip these things here. Which is to say that in a power of 2 cyclotomic, RV is just a scaling of R, as I've already mentioned. And in general, you have this kind of inclusion here. So R is a sublattice of RV, but then also MRV is a sublattice of R. So and these are almost equal, but they have, in cyclotomics, these are almost equal, but there's a slight strict inclusion in some cases. So let me skip these. All right, so now what I'd like to focus on is the actual hardness proof for LWE, or for ring LWE, that is. So the statement that we want to prove is that under a quantum reduction, you can reduce the worst case SIVP approximation on ideal lattices to decision LWE with these parameters. Right? So alpha here is kind of the noise rate, and the approximation you'll get is like n over alpha. So the reduction strategy that we'll use is rather different from the one I talked about in the previous talk. It uses the same core ingredient, the same idea of the core ingredient, which is to go from a BDD problem, use a BDD instance, and Gaussian samples to create LWE samples. But now the way that we're going to do this, we want to go now directly to decision LWE. Okay, so the idea is to now kind of fiddle with the error rate and detect when the error rate decreases. So if you remember, we have this machine which says BDD on L at distance D plus DGS samples at parameter R gives you LWE samples with basically noise D times R. So alpha q equals d times r. So this is the kind of machinery that we have before. But now one thing to notice is that if your BDD point is at distance d, and these samples are with parameter r, then your LWE noise is d times r. So what we're going to do is kind of essentially fiddle with this, okay? We're going to fiddle with this point and try to use our LWE oracle to determine whether the noise got smaller or bigger, whether the noise parameter got smaller or bigger. So when the noise parameter gets smaller, that means d actually decreased a little bit. And therefore, we've gotten closer to the lattice. Okay, so we were at distance d. We got a little bit closer than d. And then if we can detect that by using our LWE oracle, then we can continue that process until d becomes essentially 0. And we can decode the BDD that way. Okay. So we're going to play with alpha by playing with our original BDD sample. And the goal is to detect when alpha has decreased. Does that make sense? That's the overall strategy. How to implement it is going to be tricky. So let's suppose that we have some oracle which does work on LWE with parameter alpha, noise rate alpha, with some non-negligible advantage. And so we're going to define P of beta as the probability that O accepts when given samples, LWE samples with this kind of noise rate, e to the beta. Okay, so this is like an exponential. So this might be what it looks like, right? So we have some oracle. We know that the oracle has to have some good advantage by assumption at a particular error rate. But at other error rates, it may have, terrible behavior. It may actually give the wrong answer, or maybe, just flips a coin and gives no useful information. So the plot of how the oracle's acceptance probability behaves, may look like something crazy like this. However, one thing you can notice is that when the noise gets very large, okay, as the noise grows toward infinity, the oracle's acceptance probability has to stabilize. And the reason for this is if you add a ton of noise to LWE samples, it basically just wipes them out. It just randomizes them completely. So whether you add a million noise or a billion noise or a trillion noise, the distribution of the samples is the same. It's just uniform. So as you increase the amount of noise, the oracle's acceptance probability has to stabilize at some fixed probability we'll call P sub infinity. Okay, this kind of denotes how much, what is the oracle's acceptance probability on uniformly random samples. And then another property, which we'll get to, is that this graph has to be kind of smooth, has to have a Lipschitz property, because when you vary the amount of noise by a tiny little bit, the probability that the oracle, probability's acceptance that the oracle accepts can't change by too much. Okay. So again, these are the key properties of this P of beta. It's a pretty smooth function because when you have two different Gaussians whose parameters are very close, these are statistically close. So the probability of accepting can't change by too much. Let's see. Okay, as I already said, once beta gets big enough, there's some threshold, it doesn't matter too much what it is. This P of beta is basically P of infinity, the chance that O accepts on uniform samples. Okay, because huge error just randomizes completely. And then what we also know by assumption is that for the very specific value of alpha that we're interested in, okay, so for that specific value, the oracle does have advantage, has some non-negligible advantage. So that means that there's some gap between P of log alpha and P of infinity. So somewhere between log alpha and log n, basically, there's a noticeable change. The derivative of P is noticeable. And that's what we're going to kind of use as our main point of leverage to make this work. Okay, so how to exploit the oracle? As we said before, we have this quantum part, the classical part, the core component of Regev's reduction. We have a BDD instance. We have DGS samples, and we can produce LWE samples with this value dr. This non-class, right? Good. And then the idea, as I already mentioned, is let's perturb T a little bit. So we can run the oracle, we can run this experiment and query the oracle and see how often it accepts on this case. Then we can perturb T a little bit to T prime, do it all over again, and measure how often the oracle accepts on this case. Okay? And basically, we just want to check whether we got closer to the lattice over here. We want to check whether T star got appreciably closer to the lattice than T was. And we'll do that by seeing seeing how this error rate changes. Okay. So one thing to notice is that when you get closer, you end up getting a sort of a suffix of P. There's just a shift. Okay, so now it goes from, so the red part is how things would behave here, and then the green part kind of shifts it over so that it looks like this. Yes.
Be a scaling instead. You said that the error is like D times R, so it should be like a scaled version, shouldn't it?
So D, this is the absolute amount of noise, the D times R, and then relative to normalized by Q, it's dr over Q. So the error rate is like dr over Q. Is that your question?
So is it a log scale plot then?
Oh, yes. Yeah, this is a log scale plot because the definition of P here is like this. So P of beta is LW with this much e to the beta error. So the point is, when you improve, when you manage to get closer, if I've said this right, then the plot of how often the oracle accepts is shifted over, and you kind of see more of the plot. And the point is, you can detect this. You can detect it by just invoking the oracle and measuring it. And moreover, you can see all of this by actually adding more error to your samples and watching how the oracle behaves, right? So you can kind of plot it out and notice that, hey, it's shifted over from where it was before. I've improved. I've gotten closer. So yeah, that's the kind of core idea. Of course, there's a lot of technical stuff to make it work, but that's the main.
And so here the quantum variables only used to produce these samples.
Yes.
And the only thing is that we don't know how to classically prepare these samples efficiently.
That's correct. Yeah. We can prepare them efficiently for a very large radius, exponentially large in the dimension, which only helps us to solve BDD to a very tiny distance, which is not terribly interesting. It's only interesting when you can iterate and successively go back and forth between these things. Yeah. So the quantum nature of the iterative reduction is the same as before. Everything is the same. Yes.
So you're going to randomly search for a direction that is improving, but like how close in angle do you need to get to the right?
Yeah. So you need to get like about a 1 minus 1 over n factor closer to detect 1 minus 1 over linear n, let's say, closer to detect this, and also to improve fast enough to get to solve the BDD. So there's a variety of ways you can approach this. One thing is to just try all the directions parallel to the axes and take a certain step size, and one of these actually will be guaranteed to work. Or you can do a random perturbation and analyze that more carefully. So this part is was already known. But it's detecting when you've gotten closer by a suitable factor. Okay, so actually everything I've said here is about plain LWE. To make this work in the ring setting, we need to extend from a case where we have a 1 parameter of noise, right? So we have an error rate alpha, which corresponds exactly to our BDD distance. And now in the ring setting, there's actually n parameters to deal with. So there's a BDD offset, which is an error vector E. That is it's an n-dimensional vector. And what comes out when you run this similar or analogous procedure, you now have a noise which has n parameters to it. Okay? And it's basically a scaling of this offset here. So maybe in some coordinates E is very tiny, and in others it's a good deal larger. You get the same kind of shape to the error parameters here. So you get a Gaussian error rate of alpha I in the ith dimension. So let's see, it's kind of the same picture here, but these are the n noise parameters. And now things have to get a little bit more subtle. So we have the oracle's acceptance probability is p of beta, but this is now mapping a vector beta to 0, 1. Right? So this beta now encodes the n noise parameters. And now again, we can say that as, well, actually one thing which is not immediate to prove but is true is that if any single error parameter approaches infinity, then all the samples are completely randomized. Okay, so this is actually a really key fact. So if you just really crank up a single error parameter to infinity, that completely randomizes the samples. Okay, so exactly what it says here using smoothing. And so, well, there's just one catch, difficulty that kind of doesn't generalize in the way that we'd like it to. Basically, the reduction almost never produces spherical error, okay? Because there's these n error parameters, they're proportional to the original BDD offset, and those can be arbitrary numbers or have arbitrary ratios between them. So if if your oracle only works for spherical error, but your reduction can't produce such error, then the oracle is not useful to you. So the solution is to kind of randomize the parameters a little bit. We need a stronger assumption on the oracle that it doesn't just work for spherical error, but rather it works for like random errors with random error parameters within a certain range. Now, one improvement though is that we can get rid of an n to the fourth factor that with more work from LPR. Okay. So let's see. I think I will kind of tend to wrap up here. These are the main ideas. I'd like to close with some open problems that would be very, very, very good to solve. So one thing is that we have these worst case, average case reductions for ring LWE, but they're quantum, and they're only quantum. We have no classical analog like we do with plain LWE. The reason why is if you try to use the same idea that I showed you an hour and a half ago, this reduction is completely useless in this setting because gap SVP is actually easy. So deciding deciding between small minimum distance and large minimum distance on ideal lattices is trivial because the minimum distance is always large. Okay? Or you can always put the minimum distance in a very narrow range. So this reduction probably would work if you did it, but it would be completely vacuous. So it would not be useful. So we just have no ideas how to dequantize this reduction in any meaningful or useful way. So that would be great to get some improvement on, but I have no idea how to do it. Is that clear? Does that make sense? Okay. As mentioned in the last slide, spherical error is a bit of annoying. We'd like to work with spherical error. We don't want like random error parameters when we generate our LWE samples. We did manage to prove something about it. If you limit the number of samples the adversary gets, then you can kind of pay an n to the fourth factor, the amount of error, and then prove something about spherical error. But I would love to have it without any degradation or with unbounded number of samples. Certain applications, you want to give like an unbounded number of samples to the attacker. Do that with spherical error and have a proof. That would be the problem. Let's see. I guess another really interesting question is to say, we have a reduction from ideal SIVP, so that's SIVP on ideal lattices in a fixed ring to ring LWE for that same fixed ring. But between different rings, we have almost no relations between them. We can't prove hardly anything. You can prove some trivial stuff when one ring is a subring of the other, but that's about it. So completely unrelated rings, how do these problems relate to each other? Is there a better choice of ring than another? We don't really know anything about this, either for SIVP or for ring LWE problems. So I think that one thing I'd be very excited is to get an interesting connection between two unrelated seeming rings of any kind whatsoever. We don't know how to do it.
Does this have any implication, or is just?
Well, so for example, you could hope to have one ring to rule them all. Right? One ring that's guaranteed to be as hard as all the others of the same dimension or some smaller dimension, something like that, right? And then you could say, well, this ring is definitely a safe one to use. We don't really have any idea whether one ring's weaker than another or stronger than another. We just don't know.
We have quasi-rings that have.
Which rings?
Well, quasi-rings or those middle product.
Yeah, so the middle product work is like maybe a step in this direction, I think, right? Which is very nice.
A ring, but
it's not a ring, yeah, but it's something which is ring-like and does have nice connections.
For SIS, it's even more natural. You just take the ring of polynomials without quotienting.
Without quotienting, yeah. So there are steps in this direction which have certainly been made, but right now people aren't using the corresponding problem, right? They're not using middle product too much in constructions. So if you could actually prove stuff about the problems people are using, that would be great. Okay, so it's late. Yes.
Just to complete on this, there was a solution based on the middle product and the problem.
Yeah.
Some Australian company showed interest in it. So
Showed interesting things.
in this mission. So it's
Okay, cool. And what did they show?
sorry.
What did they show? Or what's the nature of what they showed?
Interest.
Interest. Oh, okay. By interest. Cool. Yeah, I like middle product learning with errors. Will you talk about it? Okay. So I do have some things I can say about middle product offline, but I'd love to really have more of this nature. Okay, that's all I have. Good evening. I guess I should ask further questions.
So Chris, if you can build all of crypto that we know from ring LWE from middle product LWE as well, it's just as good in an application sense. We don't know how to do that yet, but that would only answer your question.
Do we know how to build?
IBE, yes.
Okay. Yeah. So there's a bunch of applications which we don't know how to build for middle product yet.
Yeah.
Maybe they will come. Right.
Chris, one.
Yeah. Oh yeah.
At the beginning, you said how component-wise multiplication is not a secure operation.
Yeah. With small error.
With small error, it's not a secure operation. But then you also said that, in the canonical embedding, multiplication is component-wise.
Yeah.
Provide an intuitive explanation of why these two things are not contradicting each other.
Yeah, that's a great question, and one thing that we very frequently panicked about or freaked out about from 2006 to 2010. So what this says is, if these errors are small, then coordinate-wise multiplication is insecure. In the FFT world, like if you transfer it to the frequency domain, then this is coefficient-wise multiplication. But now the errors aren't small; they're the FFT of a small error.
If you do, is FFT or entity?
Entity, yeah, entity set.
FFT.
Okay, so with FFT, the answer is annoyingly, it's the mod Q. It's annoyingly complicated. Actually, it's not the mod Q. It's that they're real numbers now. So the component-wise multiplication in the canonical embedding is of complex numbers with like arbitrary precision. Okay, so knowing, this thing with a whole lot of precision it's not an LW, it's not a one-dimensional LW problem anymore. It's something bizarre.
But actually it doesn't even work, right? Because you don't know what, there's a q times an integer multiple hiding in here, and what does F15 do to it?
Yeah, I think maybe it's both, right? It's the mod q, which subtracts stuff from each coordinate in a bizarre way, right? After the multiplication. That's another weird thing that happens. So in other words, what I said here is true when everything's working over ZQ. It turns into like a whole bunch of independent one-dimensional LWE problems, mod Q, and that you can break. But when it's in the reals or the complex numbers and the shift mod Q is a weird thing, then I don't know what to say. Yeah. I mean, maybe this is the key to breaking ring LWE. I don't know.
I understand why technically it's secure, but then I have no simple.
No, I agree. I don't either. And we freaked out like many times thinking that this was an attack, maybe. Yeah.
Do you have some intuition to give about the parameter n⁴ on the randomization of the distortions?
So they're not really. Yeah, it's not really distortion. I don't have a great explanation for this thing. So what you'd like to do, you have a spherical noise that you'd like to kind of get close to, right? And you have a bounded number of samples, like 3 or something like that. So the point is, if you get kind of close enough to spherical, no, I'm not going to say this right. Can you help me, Noah? I don't remember this. Yeah, it's just super annoying. Yeah, it's a technical magic.
It's related to another difficulty that you put under the rug, which is that the noise distribution itself is parameterized by scalars in every different direction. And
yeah.
Scalars must stay hidden, otherwise it's getting insecure.
Yeah, the noise parameters themselves are secret. Yeah, so you randomly.
Noise parameters that are secret by public noise parameters. Mm-hmm. And so there is some kind of any divergence argument to make it go through.
Yeah, that is a good key point, right? Which is the noise parameters are secret and chosen at random from this odd gamma distribution.
Alpha is like an element from the real subfield?
No, there's no real subfield. The alpha. This alpha is just a positive number, yeah.
Yeah, but the alpha has a ring element, the whole alpha. Oh no, each alpha comes from each sample, not each embedding. Okay, sorry.
Yeah. So this vector alpha is an n-dimensional vector of noise widths, which are applied in each of the coordinates of the canonical embedding. And so you have two options. One is to bound the number of samples you give out, and then we can prove something about a fixed spherical alpha, where all the alpha i's are equal. Or if you want to give a lot of samples out, then you need these alpha i's to be random and secret before you even generate the samples. So it's rather, I mean, it's definitely a technical annoyance we would love to get rid of.
Yeah, so in terms of provable security for applications, that also limits the range of applications because
it does.
The alpha is to stay secret.
Yeah, exactly, and
the symmetric key setting that it's more.
No, I don't think it's that bad, right? Whoever generates the LWE samples in the first place would just choose these parameters, generate their samples, and then you could even forget. You could even throw these away. So that's not really a limit to the application so much as does your application want like an unbounded number of samples, right? Does the security proof require a lot of unbounded number of samples? Then I don't know how to prove this without taking a huge loss. So that I think that's the main distinction here. Okay, so that's the nature of the open problems.
What
class of rings that is studied in this LWE
Right.
context?
Yes. So it's broadened out quite a bit recently. So we can originally we chose the class of rings was the rings of integers in algebraic number fields. And now you can more generally consider orders in orders, so non-maximal orders in the same algebraic number fields. And now there's a simple proof that you can get hardness for those as well. It's an immediate, like a one-step kind of proof. I think that's the end of what's considered for what's known as ring LWE.
So mainly efficient rings. Huh?
Yes. Yes. Yeah.
To find a ring that rules them all, it could also be interesting to.
Yes. So there's some works which consider even non-commutative rings, which you can get by taking an algebraic number ring and then doing some kind of twist to it. So there's some work on that. I don't think there's any provable hardness for that case, though. So it's not well understood what happens there. But non-commutative rings are potentially of interest. Maybe those rule them all. Who knows, right? Yeah.
Is this intuition right? If you go to matrix rings, do you land at just normal LWE again?
Yes, right. So I didn't say anything about it, but by viewing ring LWE, these A's as matrices, you can interpolate between ring LWE and plain LWE by taking, let's say, a small dimensional matrix whose entries are ring elements, right? But they're arbitrary. So there's no structure among those ring elements, but the elements themselves have structure, right? So this is what's known as module LWE or generalized LWE, different name. Yes, so you can smoothly kind of interpolate between the two worlds. There's several like NIST submissions which take this approach. Small dimension over a moderate size ring.
So power of two cyclotomics are the easiest to use for no reason.
Yeah.
So do you think they are more likely to be the easiest ring or the hardest ring?
I mean, if I had to make a bet right now of $10, I would say that ultimately the choice of ring has very little effect on hardness for ring LWE, but that's just my bet. For like either for worst case or for ring LWE.
Any takers?
What's that? Any takers? Yeah, $10 free dollars. I have, like I say, my putting $10 on it shows how much conviction I have about this hypothesis. But yeah.
I put $20.
The problem is you can never claim the bet, right? Because you actually have to show a separation, like a strict separation between one or the
Put a
other.
clock on it.
Okay, so in 10 years, what will the state of knowledge? It's kind of artificial too, right? You want this to happen. Right, I mean, so like, Damien, tell me if I'm getting anything wrong here, but for a while, there was a gap in knowledge between what we could do on cyclotomics and then arbitrary number fields, and then that gap got closed again. What's that? Yeah, for like SVP on ideal. It's kind of closed or more closed. Right, exactly. So
if you have non-uniform model of computation, they are identical.
Right.
Otherwise, not.
So for a while there's a gap, and then the gap gets narrower, and maybe it'll get wider again. So, but when is it over? Right, that's the difficulty. Put a time on it, I guess.
When it's all broken.
When it's all broken. When it's all broken, then they're all equally hard, and I win the bet. Yeah. Okay. Anything else? All right. Thank you.
Okay, so I think to most token 9 carry rather than 10.